Good afternoon from Sweden, at least, and the Lignocity webinar is kicking off. Great to have you all here today. My name is Maria Hjalmar, and together with Ulrika, we are presenting those webinars, and we have invited Hjalmar and Jesper today to give us the content of the combination of lignin and electronics. I work at Lignocity as the project manager, and thanks to a 3-year-long collaboration project together with the Kristinehamn municipality, RISE, where Lignocity belongs to Sting Bioeconomy and Paper Province. We are presenting those webinars. So it's a collaborative project financed by the EU structural funds, the region Värmland, and by the project partners. And if you like what we're doing and have got examples on who and what you would like to listen to in the future related to lignin and bioeconomy, please give us a tip. And to have the best experience today during the webinar, we advise you to use the speaker's view. And in Zoom, you find that in your upper right corner. You can play around with the options using speaker or gallery view. And to communicate with us and ask questions to Hjalmar and Jesper, please type in the chat your questions. And we will take as many of them as possible. And the recording will be on until 3 o'clock. And afterwards, we will stay for another 15 minutes and have a chat very informally. So you're invited to stay for that afterwards. And that's also the opportunity while joining us now live. So great to have you all here. And first speaker out is Hjalmar. And hello, Hjalmar. Please introduce yourself and tell us what you're going to tell us.
Thank you very much. I wonder if you can see my screen now.
Perfectly well.
Yes, my name is Hjalmar Granberg. I work within the unit of smart materials at RISE Bioeconomy and Health in Stockholm. I sit in Norrköping and work with Jesper, but I think he will present himself later. I will talk about opportunities and challenges with bio-based electronics. And here, this is usually wood-based. And the idea is that we combine lignocellulose with electronics. Now, you can ask the question, is this really a good idea? In electronics, you would like to have conductors, insulators, and materials that can behave differently depending on its environments. You usually call them semiconductors. You can train them. You can tailor their electrical properties. When it comes to wood, you can only get insulators, at least to start. You can also get some kind of semiconductors, some materials that react to the environment. But from wood, as it is, nothing really conducts electrons. But if you are working with combinations, or if you're borrowing other materials from the electronic world and then mix them together with lignocellulose, you can get connectivity. Or you can carbonize wood and lignin. And one of the largest drivers for this work within bio-based electronics is energy supply. It's both harvesting, you can think about solar cells, but also energy storage. And I think both me and Jesper will talk more about energy storage, because this is an area where you really need the large tons. When we started working within bio-based electronics, we did a foresight analysis based on the number of publications from 2016 to 2018. We calculated them and we grouped them using AI in the groups that the computer chose. And there we could see that there are actually two areas, energy storage and carbons, that both are mature, meaning that you are publishing many publications per year, and the growth rate is still quite high. And when I'm talking about carbons, I mean all these materials: graphite, graphene, hard carbon, activated carbon, carbon nanotubes and carbon black. They have different properties, but mainly there is a combination of electrical conductivity and a large inner surface. And depending on application, you can choose them in different ratios. And when we talk about bio-based, we are looking for green electronics. And here we use the bio words, both bio-derived and recycled and recyclable materials, or biodegradable. And here we are struggling with the performance. So when we are talking about graphite as such, when you have extreme performance in graphite, it's comparable and even better than metals, but usually you're far off from that. And I will show you a little bit about that. And also, when we talk about especially batteries, there are lots of conflict and critical materials in use today. For example, cobalt. But also graphite, when it's mined, it's called a critical material in the EU directive. And we are developing new recycling routes and also developing processes for pilot scale production. And we are imagining using paper machines to create the large tons. And here you can see what's happening when you are combining wood with a conducting polymer. You can produce molds in this. And some of this work is presented on the green electronics are presented in these publications or DCC reports. Circularity of DCC materials, a case study, guidelines for green electronics, and also graphite materials. Can you produce that from biomass? And now I was talking a little bit about the Digital Cellulose Center. That's a Vinnova competence center involving lots of companies and academia. And we just launched the new 5 years within this large competence center. I will give you some of the results that we have obtained the first 5 years. The vision for this center is to make cellulose-based products an integral part of a sustainable digital society. Lots of buzzwords combined together. So the DCC phase 1, we have these academic partners, KTH, RISE, Linköping University, and lots of industry partners, both from the cellulose side and electronic side. Alström, Sjöbille, Korsnäs, SCT, Borregaard, Stora Enso, 4E Antenna, Stena Recycling, Ligna Energy, Hitachi, Agfa, Grafmatech, 2D Fab, Benelli, and Mycronic. And we combined our efforts into 6 projects, and they look into different parts of the electronic or the cellulosic side or the interaction between them. And then everything is demonstrated here in a cross-disciplinary project for demonstrators. I will go through some of these results. I was talking about carbons as a special class materials which you can produce from wood. And here, depending on the precursor, you can end up with something that's purely graphitic up here with graphene layers put together, or graphitic parts that are put together with voids and pores. And you usually call this hard carbon. Depending on the application, you would like to end up here or here. When it comes to energy storage, you would like to intercalate ions in the structure. So you usually would like to end up here. When it comes to connectivity, this material is much better. So when it comes to biomass, it's considered that you can only produce hard carbon, but there are new methods aiming at increasing the graphitic part of the carbons. And here is a review of what has been done before. So with increasing heat treatment, you usually can end up with more pure graphitic structure. like here, but you can also fail and end up here. When it comes to biomass, you usually focus on the low temperature materials, since it's not considered optimal for graphitization. But now things are opening up. So these low temperature, everything below 1000 degrees is considered low temperature, uses then less energy, and perhaps you can obtain these extreme values. For example, producing this based on the electrochemical graphitization method. So while you're heating up your sample, you're also driving a current through your precursor. It could be a lignin in this case. So that means you're introducing some kind of structure, and this ends up, if you do it right, as a graphite. And this can be done at low temperature. That's what we are doing. This is still work in progress, so I don't have the results to show you today. But we can also look at the graphene cellulose interaction. So here you have a graphene flake. Many of these together makes up a graphite. And then the nanocellulose, as this one. This is a hydrophobic and this is hydrophilic. If you mix them, these will stick to the graphene. So you can end up with a lot of synergetic effects. One of these effects is that you can actually disperse graphene in water. And when you can disperse graphene in water, you can also make water-based processes such as paper. And here we show a paper containing lots of different carbons that was produced in Ahlström Munksjö's pilot paper machine facility in France. And this got large attention from Vetenskapens Värld and branch media as well when it comes to energy storage. But we can also produce this pure graphene paper. And here the fantasies puts the limits to what you can do. For example, if you convert it into a box, you can make a Faraday cage. So if here you have the graphite paper inside this board. So if you put your mobile phone inside here, nobody could call it. So you can keep it in a quiet room, for example. Or you can use it to heat up your coffee. The inside of this coffee sleeve is made of graphene paper. We've also looked at the interaction between P.PSS, which is a conducting polymer, the P dot, and then cellulose. These stick together. Here to the left, you can see the nanocelluloses as a network. And when you add the P.PSS, these end up as beads like this. This means that you can end up with a network, a conducting line, which is good for a high conductivity. We have also compared this to simulations and we got really good results, which can predict what's happening in a more complex environment. And we combined all this into a design where we actually can 3D print cellulose together with a conducting polymer. And here you can end up with both electronically conducting and ionically conducting material. And these can be applied, for example, as hydrogels for heart patches. These ones censor the heart rate. And these results are really, really good. So the partner Benelli here, they would like us to continue working with this. Also, Essity is printing the material in the diapers for sensings. We've also made an upscaled version of this in a paper machine-like process to make a film of the material. Here you can see the 3D printing. And on the left-hand side, you can see the academic work, and on the right-hand side, the industry work. So we'll end up with a dual excellence. We are now starting with the DCC phase 2. It's open, so if you would like to join, please ask me or Jesper afterwards. And here we will focus less on pure cellulose, but more on lignocellulose. And I guess that's why you're here. You're interested in lignin. So when we started the Digital Cellulose Center, we thought that cellulose with its structural properties is what's good in wood. But now we found that also lignin can play a major part when it comes to electronics. We also look into different combinations of conducting polymers and different kinds of carbons. Can we use them as electronic glues, for example? We will not only look into the passive side. So if you produce something, how can you cycle it or recycle it? But we will do it proactively. How can we design already from the start something that's good for the environment? And here the demonstrators will show us and the world what can be done with this new type of electronics. We will also create 3 new value networks, one within medtech and health, one within energy storage, and a third one within the Internet of Cellulose Things. These will hopefully create a pull so that we can communicate with the basic research and the industry research. The same goes with scalability and producibility. We will do more pilot trials to scale up our methods to see where the bottlenecks are so that we can feed it back into the basic research. And that's all I have for now. And I would like to leave the word for Jesper.
Thank you, Hjalmar. This is highly interesting, definitely. And Jesper will take over since yet we don't have any questions. So we let Jesper continue, and I'm sure there will pop in some questions. And since your speaks are related, then I'm sure we can combine them afterwards. So thanks for sharing, Jesper. And please introduce yourself also, so we get to know who you are.
Yes, let's see. Can you see my presentation all right now?
Perfectly well, thank you.
Perfect, great. Yes, so my name is Jesper Edberg. I'm a researcher also at RISE Research Institutes of Sweden, working in Norrköping in a unit called Bio and Organic Electronics. And we also in Norrköping have our sister unit called Printed Electronics, so we work basically as a single unit here. And just a few words first about printed electronics, since it's also linked to many of the applications I will talk about today. Printed electronics is basically a technique for producing electronics on thin and flexible substrate using printing techniques, for example, inkjet printing or screen printing. So the materials that we are working with are soft as opposed to classical electronics, which uses hard materials like hard plastics, metals, and semiconductors. And with this technique, you can do things that's not possible with classical electronics. For example, you can have thin and conformable electronics that could, for example, be worn on the body, or maybe you can fit it into areas or volumes that are usually not possible, like inside the walls or floors of smart buildings. But back to the topic of today, which then is about how we can combine forest-based materials like lignin with electronics to make more sustainable electronics. But to start with, why do we care about sustainable electronics? It all comes back to the problem of electronic waste, I would say. Electronic waste is one of the largest growing waste streams. It's very difficult to recycle many types of electronic devices because they are very complex. They contain a lot of different materials and are built in a way that they are often difficult to disassemble at the end of life. They also often contain very hazardous toxic materials like heavy metals. And in general, we are pretty bad at actually taking care of our waste. So we're creating roughly 50 to 100 million tons of electronic waste every year now. And also it seems like of the people that actually take care of their waste, a lot of it is exported illegally to low and middle income countries. So there's also problems with the regulation around how to handle electronic waste. I will also talk quite a lot about carbon in my presentation. Hjalmar already mentioned this. So why are we so interested in carbon? Well, for one, like Hjalmar mentioned, it's a way of, we can use wood and turn it into carbon. And carbon is used in many different applications, including many electronic applications. And one of the fastest growing areas perhaps is in batteries. So as you can see on the graph to the left side, the battery market is exponentially growing. And this is largely a response to the transition from fossil-based energy sources to renewable energy sources, and also the electrification of the automotive industry. So we will need more and more batteries in the future, and graphite and other forms of carbon are usually a component in these batteries. So for example, the very commonly used lithium-ion battery uses graphite in its anodes. But you can also see in the graph to the right that there will pretty soon be a shortage of graphite. We have not really hit this shortage yet, but in the coming decade or so, we will start to see a big shortage in graphite and other carbon-based materials. At the same time, there are some problems with graphite and other carbons as they are produced today. So they are very energy-intensive production, often sourced from mining, which has its own big environmental problems. It can produce many types of dangerous particle emissions and also use very toxic chemicals in this production. And we're also at the same time seeing more and more regulations about having sustainable production methods and sustainable products, and also regulation about what we can call green electronics or green production. So this is something that will impact all of us in the coming years. So back to the question then of how we can use forest-based materials as a better source for carbon and other components in electronics. So my first examples here, I will have a series of examples of how we have used lignin. Largely, this research comes from the Digital Cellulose Center, which Hjalmar presented a little bit about. I work both as a product manager and as the scientific leader in DCC. And one of the research tracks there is about graphitization of lignin. So Hjalmar showed two ways of doing this. You can use basically high temperatures, like in an oven, and you can also use an electrochemical method. But one more way to do it is to use a laser. So it's basically the same principle. You heat up the lignin to very high temperatures, but you do it much more locally. And you can actually write patterns into lignin and other bio-based sources and convert it into graphite or even graphene. So we published this research a couple of years ago. It's a paper called Laser-Induced Graphitization of a Forest-Based Ink for Use in Flexible and Printed Electronics. And this is also why I mentioned a little bit about printed electronics, because in printed electronics, we often use carbon-based inks to make these printed devices. But the carbon in these inks is made from a mixture of graphite and carbon black, which comes from mining and oil, so they're not very sustainable. So we wanted to see if we could combine these three things using forest-based materials, using laser graphitization, and combine this with printed electronics. And we did this by formulating a printable lignin ink, which we then could coat using printed electronics. And then we applied the laser on top of this to turn the lignin ink into conductive carbon. Here you can see the lignin ink and also how this printing equipment looks like, the frames with the pattern that we're printing, the printing equipment, and how a pattern can look like when we have printed it onto a substrate. And then we just use a commercial carbon dioxide laser to directly write the carbon tracks onto these lignin prints. And what's interesting about this technology is that the laser itself uses very low power. So this laser is only 30 watts, and actually we only use 10% of the maximum power, so just something like 3 watts. And compared to the oven graphitization, where you have to reach maybe 1,000 to 2,000 degrees, it's very low power consumption. So in and by itself, that's also a step towards more sustainable production of graphite. Quite a lot of details on this slide. It's about the crystal structure, so basically the quality of the graphite that we're forming. I'm not going to go into the details, but we did see that we form very high quality graphite. So we have formed very big crystallites compared to many other publications, which is good because larger crystallites correlates to higher conductivity. And we also see that we have a high degree of graphitization. And in some cases, we could even produce graphene, multi-layer graphene, depending on the laser setting and the material composition. So what can we then use these, the carbon that we have produced? How can we use it? One way that we have applied it is to make humidity sensors to sense moisture both in the environment, the surrounding air, and also inside of wood elements. Wood is, of course, a very good building material, but it's also biodegradable and it's sensitive to moisture, because you can get rotting and mold formation. And there's a lot of structural damage every year in buildings because of moisture damage. And also it's a health hazard, of course, if you get mold in your building. So we would like to monitor the health of the building by integrating humidity sensors directly onto wood elements. So we use this laser graphitization technique and directly made these humidity sensors, which is manufactured directly on the wood. So it's the carbon itself comes from wood, the sensing element is made from wood, and it's made on wood to measure properties of wood. So it's wood, all about wood here. What we could see was that we can both measure the surrounding air moisture, and we can also track the spreading of moisture inside of the wood, and we can separate the two properties. We will see here if I can make this video work, so we can get a live demonstration. Yes, so what we're seeing here is actually a steam being blown onto the sensors. And as you can see, this indicator, which is just an LED array, is showing that the moisture content in the air is increasing. So this could in the future be used in an IoT, Internet of Things way to monitor remotely the moisture content inside of buildings. Hjalmar talked a lot about energy, and there's energy storage, but there's also energy harvesting. So how can we generate energy in new ways? And of course, we are switching to more and more renewable energy sources like wind, solar, and hydropower. Most of the energy harvesting technologies, however, is based on only one of two ways. There's solar power, which converts electricity directly from sunlight. And then all others are really based on, in one way or another, rotating a dynamo. So in case of wind power, of course, it's the blades turning, and in a coal or nuclear power plant, you're heating up water, which is then turning into steam and turning a dynamo. But there is a new contender, which is based on a completely different type of technology, which is called triboelectric energy harvesting. So it's based on static electricity. So for example, if you rub a balloon against your hair, you know what happens. And in a dry winter day, you might get an electric shock if you touch a metal object. So this is static electricity. And then the question is, can we use this static electricity to harvest energy? And the answer is then, of course, yes, and we can do this. So we have explored if we can use forest-based materials for these type of energy harvesting technologies. The energy really comes from the friction between two materials, and you can use quite a wide range of materials, including then bio-based materials, but it's a little bit more challenging to work with these bio-based materials. In this work, we used a chemically modified form of cellulose, which is called nitrocellulose, and also lignin to make nanofibers through electrospinning. And we made these fibers in order to get as much friction as possible, really, when we push these materials together. You also need some conductive parts in a device like this. So then we use the same lignin fibers and carbonize them. So this was an example of what we think is the first fully bio-based energy harvesting device. And from just pushing, you could say, you apply pressure to this device, you can generate up to 370 volts or more in the research that we showed. You can also use this type of device as a sensor. So here we put the sensor, the 100% bio-based sensor, into a smart package, and then it works as an impact sensor. So if you have transported a package, you might want to know if it has been dropped at some point, if it's a sensitive material inside. So then we have applied it under the package, and we have developed an app which can then track if the package has been dropped. So if it's dropped, the pressure of the impact is converted into an electrical current, and this is then detected by the electronics. The good thing about this is that if you're gonna put electronics into normal packages, then once again you end up with this problem of electronic waste. But if you can make the electronics from the same material as the package is made of, then maybe it's not a problem at all. And you can think even larger than this. Maybe in the future we can use these triboelectric materials to make really large-scale energy harvesting similar to the wind power that we have today. But then we have imagined something more like triboelectric flags that will be fluttering in the wind, and from the movement of those flags we will be generating electricity. But then if we have all these renewable energy sources, we also need to be able to store this energy. The problem with renewables is that as opposed to, for example, nuclear or coal power, the wind blows when it wants to, and the sun is only up in daytime. And actually, it's mostly at nighttime or evenings that we need this energy. So it's intermittent energy sources, and we therefore need to store the energy for some time until we need it. So we need something in between here, and that is energy storage in the form of, for example, a battery, supercapacitor, or another energy storage technology. And we need to produce enormous volumes of these energy storage devices in order to meet the future demand. And we believe that using techniques like paper making could be one way to reach this goal, because paper making is an incredibly fast manufacturing technique. You can shoot out something like 100 meters per minute or so, or maybe more. And we have shown that it's possible to make some of these type of devices, batteries and supercapacitors, using a combination of paper and cellulose and printing techniques. But to further increase the energy storage capacity of these devices, it's actually possible to use lignin, because lignin can directly store electrical energy through an electrochemical reaction. So we showed that we can increase by up to a factor 10 the energy storage capacity of these type of batteries and supercapacitors by adding lignin. And also we have shown this for other type of materials which comes from the forest. And this slide was actually meant to take out, so I will skip that one. I also wanted to show that this is not only happening in our labs, but it's also happening in industry. So there is one company called Ligna Energy, which is a spin-out from the research from Linköping University and RISE, which are now producing lignin-based batteries for both small-scale and large-scale energy storage applications. And besides storing energy directly in the lignin, as we have talked about a lot, you can convert lignin into carbon, for example, hard carbon, which can be used for lithium-ion batteries. And this is something that we have seen that Stora Enso and Northvolt has teamed up to do. So they have produced a new battery called Lignode, which is then lignin-based hard carbon lithium-ion batteries. So most of this research that I've presented was from the Digital Cellulose Center, but I would like to also briefly mention another project which recently started. It's an EU project called Hyperlignum, where it's all about wood. It's about exploring wooden materials in hybrid printed electronics. So a holistic approach towards functional electronics with net zero carbon emissions. And the project is coordinated by RISE, and the coordinating project leader is Valerio Bene, who is a colleague of mine working here in Norrköping. So it's a number of different countries and institutes joining this project, which started late 2022 and will be running through 2026. It has a budget of over 6 million euro. Some of the ambitions of Hyperlignum is to propose and demonstrate a holistic approach for the manufacturing of electronics with net zero carbon emissions using wood, to demonstrate the use of low impacting materials in the manufacturing of functional materials and components, to develop processes for the additive manufacturing and integration of electronics systems within wood and wood products, to exploit sustainability analysis, so LCA, as a decision-making tool for the design of green and circular electronics, and finally to contribute to the consolidation of the definition of green and circular electronics, because there is today not a clear definition of what we mean by green and circular electronics. And then just a quick snapshot of what this project aims to achieve. So here you see a number of demonstrators, for example, sensors integrated into wood construction elements. So it could be, once again, moisture sensors or strain sensors. You could also integrate electronics into furniture, for example, for measuring environmental parameters like carbon dioxide levels in an office environment. And then the electronics will be completely hidden inside of the furniture, and it will be powered without any cords. We will also look into how we can more easily separate materials for easier recycling. And one of the more ambitious goals is to make what's called an eco PCB. So a printed circuit board, the type of circuit board that you usually see inside of a computer, but made on wood instead of the plastic cards that you will usually see there. There are several work packages in this project. I will just mention a few words about each one. So it's work package 2 on the bio-based building blocks and conductive fillers. So this is basically how do we take wood and make the building blocks that we need for the electronics. Work package 3 is about inks and adhesive substrates, coating and impregnations. So how do we take these building blocks and make them into functional inks and coatings? Work package 4 is about the processes and components that we then make from these inks. So we will largely use printed electronics like inkjet printing and screen printing to make devices like air quality monitoring, microchips, and also lignin-based supercapacitors and other forms of energy storage. All right, I think that actually brings me to the end of my presentation. So just some acknowledgements. First of all, the Digital Cellulose Center and our members. This constellation is actually from the first phase, the first 5 years of DCC. Like Hjalmar mentioned, we're now moving into the second phase, phase 2 of DCC. So the company and partner constellation will look a little bit different. And also, of course, our funding agencies. And if you have any questions about the Digital Cellulose Center or Hyperlignum, you can contact me or Hjalmar or Valerio. And both projects also have their individual web pages if you would like to get some more information. And DCC also has a Twitter page if you would like to follow us there. So thank you very much.
Thank you very much. Very interesting and very well presented from both of you. And I have you spotlighted the two of you, so I hope everyone can see you. And now the questions are popping in. So here we go. Does it matter from what wood species the lignin in the laser form graphite comes from? And what counter ion is used in the lignosulfonate?
Yes, we have tried a couple of different forms of lignin for the laser graphitization. The one that worked the best for us was lignosulfonate, so sulfonated lignin, but it's unclear if that is because of the specific molecular structure or if it's more about that it was a molecule which was easy to form into an ink, and then we had a high quality of the prints. It's a bit difficult to separate the two. So I think in this phase 2, we would like to look deeper into what's happening down at the molecular level when we do this type of conversion from lignin to graphite. And I think we have been talking, Hjalmar, about maybe synchrotron experiments, if it's possible to actually investigate while doing the carbonization, the process itself. As for the counter ion, I think it is sodium. Could be in the acid form, but I think it's sodium, which is the counter ion. Yes.
Great, thank you. And next one, how the laser converts the lignin to graphite graphene. How is the conductivity and hydrophilicity of the prepared graphites? Does it depend on the nature of the lignin or the power of the laser? Many questions in one.
Yes, let's see if I can remember all of the ones. So the first one, can you remember what was the first one?
How the laser converts the lignin to graphite graphene?
Yes.
Yeah.
So how does it work? Well, it's basically the same as with the oven graphitization. The laser very locally and for very short amount of time. It's a pulsed laser, so for a very short time it heats up the material to very high temperatures. We haven't measured this temperature exactly. It's very difficult to do that. But from the quality, let's say, of the graphite that we're forming, we can kind of expect that we reach something between 1,000 and 2,000 degrees Celsius. So that is how it's formed. Yes.
Maybe I can comment here as well. Yeah. We know what is happening. The laser is heating up the material, but it's only heating up the top layers. And we are also removing a lot of volatile organic compounds. So depending on what's left, we will end up with different morphologies. And usually we end up with more graphene-like structures. And this is supposed to be hard carbon if you would have used a furnace. And here it's a little bit new. We are still considering and optimizing all parameters using oxygen or other gases to see how we can impact the structure. I would say not everything is known here.
And I think one question was about the conductivity.
Correct. How is the conductivity and hydrophilicity of the prepared graphite?
So the laser one, we get something like 30 to 100 Siemens per centimeter. But then we should also remember that the material that we're obtaining is very porous, actually. So like Hjalmar said, there's a lot of volatile compounds in this material. So when we do the graphitization, it kind of blows up like a popcorn popping. So we end up with a very porous material. And most of the volume then that we're measuring on is air. So you can kind of compensate for this to determine what would the conductivity be if you had a very compact film. And then we believe it could be much higher. But we're still working on how to get rid of these volatiles in order to get a more dense film for high conductivity. But sometimes it's actually very good to have a porous film, so for example, for energy storage applications. So depending on the end application, you want more or less porosity. And hydrophilicity, I'm not sure if we have actually measured that, but I do believe it's quite hydrophilic. I think some of the graphene papers and other materials you have worked with, Hjalmar, is more hydrophobic, but because of the porosity.
I wouldn't count on it. We haven't measured, so we don't know that one. But when it comes to conductivity, I would like to say that this is much better than printed electronics based on carbon black. So the laser graphitization is better than what we are using today in printed electronics.
And I would also like to brag a little bit that at least in terms of sheet resistance, I think we have the world record still for lowest sheet resistance using the laser graphitization technique. Someone might have beat us since last time I checked, but at least for a while we had the record.
Congratulations. And the last, let's say, question that went together was, does it depend on the nature of the lignin or the power of the laser?
So power of the laser, definitely. We have seen higher laser power, higher conductivity, but at some point you start to get cracks in the film, which is probably because of these volatiles. So we haven't really been able to push the technique to its maximum, I don't think.
Yes, and we are trying also to use charring materials, other catalysts that can help the conversion as well.
Great. And the next one is, do you do any work on wood-based thermoelectrics for energy harvesting, or any thoughts?
We have done some work on thermoelectrics. At the time, it was more cellulose oriented. So we were mixing conductive polymers with cellulose and making structures like aerogels for thermoelectric energy harvesting and sensing applications. I'm not sure if it's been done on wood. I know that maybe some research is also done in the Granberg Wood Science Center, which is closely related to us through joint researchers. I don't know, Hjalmar, do you know?
I would say that the aerogels, they are made on wood. So yeah, depending on what you count as wood. So it's not in its natural form, but we are making non-cellulose and then we're freezing it and we're cross-linking, and then we can make these thermoelectric generators. That takes.
Great, thank you. Are lignosulfonates better starting materials for these applications? What about other lignin sources like kraft lignin or sulfur-free lignins?
Yes, I think I partly answered that question before, that we don't really know if it's the structure of the lignin itself that matters, or in our case, it was more the ink preparation. We did try to use softwood kraft lignin. We could form an ink and we could print it, but we saw that instead of graphitizing, the material kind of just evaporated. We ended up with nothing on the surface. And that could be because it's more particles, larger particles, loosely connected. And then when you heat it up, they just kind of disperse so that they're not really forming a continuous film down at the molecular level. So we will continue to investigate this and try to separate the structure on a nanoscale from a macro scale.
Maybe you can comment on the high how it dissolves in water. So lignosulfonates dissolves in water. So if you put them in batteries, they tend to end up on the other side. If you start at one electrode, they can end up at the other side because they can migrate. So we are also looking into different kind of lignins that are not water soluble.
Right, thank you. And could biomass collected from grasslands also be used to produce lignin used in electronics?
We haven't looked into it, so we don't know. This is a quite new area, I would say. We are spanning out the application field of applications, and we're also looking into different raw materials, but I think that will come as a second in the second round when we know what we are looking for.
Yeah, I know that at least for the graphitization, there are many types of carbon-rich polymers and molecules that can be used for this type. It's not limited to only lignin. It's just that we have seen that lignin works very well, and that's probably partly due to the higher concentration of carbons. And then also for different type of lignin sources, like if it's wood or grass, then you would have different amounts of lignin, I would assume.
And different classes of lignin too.
Different classes, yeah.
Great. Next question I can even respond to myself. If there will be a recording available of this webinar, and yes, it will. And you can also find earlier webinars either on the YouTube channel from Lignocity or on our webpage, also called Lignocity. So it's a lot to find out about lignin there. And then we move on to, in your opinion, can it work as hybrid electrode for electrocatalysis?
Sorry, I think I missed the beginning of the question. Could you take it again?
In your opinion, so what do you think? Yeah. Can it work as hybrid electrode for electrocatalysis?
I don't really understand the question either.
I don't really fully. I'm trying to see if I can read
it. You read it yourself in the chat. It's perhaps easier than to.
Let's see if I can find it.
It's quite at the bottom.
There we go. Can it work? I'm not sure which part you are referring to here. If it's the lignin itself or the carbon made from lignin. Maybe the person asking the question could clarify.
Yeah, we either type it in again, or the carbon from the lignin, yes.
Absolutely. I would say that for electrocatalysis, I think you want to have a very high surface area, so something maybe closer to activated carbon than the very dense graphite. I'm not an expert on electrocatalysis, but we do have experts on electrocatalysis within the Digital Cellulose Center. It's not something that we have really explored yet, but might be interesting in the future. But since we know that the carbon that we're forming is very has both a combination of high conductivity and large surface area, I think it could be very useful for this.
Thank you. And have you used standard lignosulfonates or modified purified lignosulfonates?
Ooh, good question. It's not something I have modified myself, at least. It's bought just from Sigma Aldrich. So lignosulfonate, sodium salt. Maybe Hjalmar knows something about it.
No, I don't know.
I would guess it's standard lignosulfonates, not sure.
We will assume that until we know better.
Yeah.
And that was so far the last question. There are still some minutes to type in your question if you feel like. And I'm curious and ask each of you, what is the most important takeaway you will give us as listeners today? If I'm asked tomorrow, what did they tell you? What would you like me to respond, Jesper?
Oh, that's a good question. Most important takeaway.
I can take it while you're thinking.
You start and I think a little bit.
So I try to calculate on the back of an envelope here. What will be the market for batteries in 2050 based on Elon Musk? And I calculated like 50,000 billion kilos, so 50 billion tons. And if a third of that is graphite, like in a lithium-ion battery, there is plenty of material. So here we have lignin. It's a good source to make graphite or graphene. And I guess there is plenty of room to play here to fulfill the gap that Jesper showed. What's happening after 2030.
So we are in the beginning, so to say.
Mm.
Thank you, Jesper. Your most important takeaway.
Yeah, maybe on the alarmist side, and once again the topic of electronic waste. That if these projections are true about the exponential growth of, for example, batteries, then if we don't start handling them in a better way, then we are heading for an even bigger environmental disaster than we maybe already have. And I do believe that forest-based materials and also the new processes that we are suggesting, so not just the material itself, but also the sourcing and the production methods, will be necessary to not end up in this really bad situation.
Great, thank you. And how long was the project meant to be now, the second part of the DCC?
So 5 years from now, it's essentially 2028 then, or 2027, I guess.
So
yes, and then after that, we hope that we will find further funding and that the project or the center will be continuing even after that.
Sounds great. And I hope everyone listening today has a lot of new input and take this with them and spread the word about the opportunities. And I will announce that we have a next webinar on the 9th of May. A colleague from us at RISE, Jerk will speak, and together with Justin Charmelot from Bloom Biorenewables. So the topic is elastomeric materials from lignin. So the 9th of May, and we will send out invites for that in a close future. And I think everyone is happy with what we have learned today. So thank you so much for taking your time. And for those who want to, please stay for another 15 minutes and we will have an informal chat that is very appreciated. But the formal webinar will end here. So thank you. And we do record and it will be broadcasted as well in a close future. Thank you very much.